All right, so at this point, I'd like to take a moment to step back and review a couple of the terms that we have relating to electrical forces. Okay, so the first that I want to talk about is the electric force. Okay, so force, like we've seen before, is a push or a pull. And these are measured in newtons. These are forces exactly like the sorts of things that you studied in 121. I don't want you to get confused about it. These are, pretty familiar in that regard. Now, the thing that's new is that the electrical forces are exerted between what we call electrical charges. Okay, so charge is this property or quality of particles like protons and electrons. Protons are positively charged, electrons are negatively charged, and those are what we're talking about when we talk about charge. So a charge is not inherently related to forces. You could have an attractive or repulsive force on any charge. It's just this property that certain objects have and that certain particles have that through experiment we determine influences the electric force that shows up. Okay, so we label these two types of charge, positive or negative. And as you thought about last week, there's not really any reason why 2 is the magic number. We could have 3 or more. It's just from observations, it seems like 2 is the right number. Okay. We can also quantitatively calculate the force between two charges. Okay, so for that we use Coulomb's law. So the force is equal to the product of the two charges, Q1 times Q2. There's some constant out front, K, and then it's divided by the distance squared. And then the direction here is either toward or away, so just depending on what the combination of charges are. And if you want to, you can actually make this really mathematical by defining which direction r goes, either from 1 to 2 or 2 to 1, and then use vectors. And if you were, for instance, coding this, you would want to do it that way so you don't have to think about it. It would just happen automatically. Okay, so if we imagine a situation where we have some sort of, let's say, constellation of charges, maybe we have a positive charge over here and a negative charge over here, and maybe a positive one here and a positive one here. We could have any number of charges in this situation. And let's say that I pick charge 0. Okay, I'm going to call this one 0, and I'll call the other ones 1, 2, 3, and so on. If we had more charges, we would just name however many there are. And let's say we wanted to find the net force on charge 0. Okay, so if we want to do that, then what we have to do is we have to consider the forces from each other charge. Okay, so for instance, charge 1 is going to exert a force on charge 0 this way. It'll be a repulsive force. Charge 2 is going to exert a charge this direction. That'll be an attractive force. Charge 3 is going to exert a force in that direction. That's going to be a repulsive force, and so on. So we just consider them one at a time and add those all up. Okay, so going to take the force on 0 by 1, going to add the force on 0 by 2, going to add the force on 0 by 3, and then you would just keep on going until you added up all the charges. Okay, so this fairly straightforward equation belies the fact that these are all vectors, and it's actually kind of hard to add vectors together. So if you wanted to actually do this in practice, what you would have to do is you would find, say, the x component. So you'd find the net force on 0 in the x direction, and that would be calculated by the force on 0 by 1, which will be k q0 q1 over r01 squared. And then there'd be some angle involved. Okay, so I'll just name everything relative to the x-axis, and then maybe I've got several different angles involved here, one for each of the particles. So if I wanted the x component, and I'm measuring everything relative to the x-axis, then I would have, say, cosine of theta 1. Okay, so first I find the magnitude of the force from charge 1, then I find the x component using trigonometry. Then I would have to repeat that process for each other of the forces. So I would do k, q0, q2 to find the force from particle 2 over r02 squared, and then I would use its angle, theta 2, relative to the x-axis to get that x component. And then you would keep going. Okay, and then you would repeat that whole process for the y component, you'd repeat that whole process for the z component, and eventually you end up with the total force. Alright, so what I want you to take away from this is that this sounds like a nightmare. This seems like a lot of work, and we want to simplify this process as much as we possibly can. Alright, so a couple of things to notice here are, first of all, we're treating charge 0 a little differently than we're treating all the other charges. Okay, so charge 0 is present in every one of the terms. It's not just present in the first term. That's one way that we're treating it differently. Also, if we change one of the other charges, if we change charge 1 or 2 or 3, it'll make some small difference in the overall force. But if we change charge 0, that will change everything. Okay, so for example, if we take charge 0 and we doubled it, so we take it to 2 times charge 0, then the net force on 0 will double. Okay, and similarly, if we took charge 0 and we made it negative, then the F net on charge 0 reverses. Okay, so even though that charge turns up in every single term, there are some patterns. And if we make some changes to that charge, we don't actually have to redo the whole calculation. We can just see how it will change. So this suggests a way that we can simplify this process. Instead of having to consider all the pairs of charges, maybe we can factor out the effect of charge 0. Okay, so that's where the idea of an electric field comes in. Okay, so we're going to define a new quantity. The electric field, which will be capital E vector, is going to be the electric force divided by charge 0. Okay, so we're just dividing out the effect of that charge. It showed up in every term anyway, so we can ignore it, essentially, when we're calculating the electric field. Okay, so what's nice about this? Well, if I know the electric field, then I can use this equation backwards, and I can find the electric force by taking the charge times the electric field. Okay, so I'm basically separating the effect of charge 0 from the effect of all the other charges. Okay, so E here is called the electric field. And we'll talk a little bit more about how to interpret it as we go. But for now, that's what we need to know. Its units we can figure out from the equation. It's just going to be units of force divided by units of charge, so newtons per coulomb. Okay. All right, so I told you that we're treating Q0 a little bit differently. So there's a name for the distinction between Q0 and all the other charges. So Q0 is the test charge. That's a pretty common name for it. But you might think of it also as something of a probe of the electric field. So we might call it a probe charge. Or the way I like to think of it actually is as the passive charge. Okay, so the reason for that will make a little bit of sense when I give a name to what the other charges are. Okay, so all the others are going to be either the source charges or another common name is the environment charges. Or you might think of those as the active charges. Okay, so essentially you can think of the other charges, 1 through 3, as creating an electric field. They're the ones that are pushing on charge 0, and charge 0 is along for the ride. It's not pushing on anything else. I mean, we know it is, but we're ignoring that part for now. We just want to know what happens to that charge. So the other charges are the environment. They're pushing on charge 0. They are actively making anything happen, whereas charge 0 is just passively along for the ride. Okay, so we can think of then the charge 0 as being essentially just a probe. It's the way that we figure out what's going to happen. All the other charges are the ones that are doing things.